if we have a box that's, let's say, moving, along at a constant velocity, we know that box contains kinetic energy. And the kinetic energy, we know the equation for that as kinetic energy equals 1/2 mv squared, right? So the kinetic energy is dependent on the mass of the object and its speed. Now there's another measure of sort of the energy of a moving object, and we call that momentum. And you probably have some idea of what momentum is already, sort of in your head. You've heard that term before. And momentum refers to more how difficult it would be to stop an object from moving. The equation for momentum, first of all, we use P as the symbol for momentum, and the equation is mass times velocity. Notice how it's a vector. And that's it. So you'll notice it's sort of similar to the kinetic energy equation in that it has m and v. And in fact, when you learn a little bit of calculus, you'll notice that the relationships between these two is actually very close. But anyways, so it only is reliant on mass and speed or velocity. And there's a good reason why we sometimes use momentum instead of kinetic energy. And we'll get more into that in the next lesson on conservation of momentum. But for now, all you need to know is that momentum is equal to mass times velocity. It's also a lot simpler than the kinetic energy equation, right? And it's a vector which can be useful in different ways. So every object that is moving, that has mass, has a momentum associated with it. So doing a very quick example here, let's pretend that this box has a mass of, 10 kilograms. And let's say it's moving at 2 meters per second in the east direction. So we can calculate the momentum as just the mass times the velocity, right? So it would just be 10 kilograms times 2 meters per second east. So the momentum of this box would just be 20 kilogram meters per second east. And let me just put a little dot in between the kilogram and the meters per second. So the units for momentum would obviously be kilograms times meters per second, or just we call it kilogram meters per second. Okay? So it should be clear here that if a box or if an object is heavier, it will have more momentum, and if it's moving faster, it will also have more momentum. Okay, so what's the difference between momentum and impulse? Impulse is a new word. Impulse is actually very similar to momentum, but we usually use J for impulse, and what J is just a change in momentum, right? So if I add momentum to an object by speeding it up, that is considered an impulse. So how do you speed an object up? Well, you apply a force to it. And you're going to apply a force to it for a certain amount of time. And another way to look at the equation for impulse, we can say it's a force applied for some amount of time. And you may be asking yourself, how is a force times time going to equal the same thing as a momentum? The units, you should see, should be the same for this and this, right? Well, let's think about the units for force times time, right? That would be newtons, seconds, right? But we said momentum is going to be something like kilogram meters per second, right? Are those the same thing? Well, we can actually break a newton down, right? Remember, a newton is a unit of force, and sort of the most common equation for force is mass times acceleration, right? Newton's second law. If we think about this, a newton, what is a newton? Well, a newton, mass would be measured in kilograms, and acceleration is meters per second squared, right? So a newton is just a kilogram meter per second squared. So if we replace the newton in here with a kilogram meter per second squared times seconds, you should see what happens. The seconds will cancel out with that second squared, and what are we left with? Kilogram meter per second. So interestingly, we can basically find momentum in two ways. And one is a force times a delta t, a time, an amount of time. And this gives you the change in momentum. And a momentum, to find like the absolute momentum, the momentum an object has, you just need to multiply its mass times its volume. So just to see a very quick application of this, if we have this same box, right? And let's say, so we already know the box is moving along at 2 meters per second. It's got a momentum of 20 kilogram meters per second. What happens if we give that box a push as it's moving? And let's say we push it with a force of, 100 newtons for 1 second. So let's say we're going to add an impulse of 100 newtons for 1 second. What that means, so our J is just going to be our, It's our force times our time, right? So it's just going to be 100 newtons. And what I should have said, let's assume we're applying this force in the same direction the box is already traveling. So east, right? Times time times 1 second. So the impulse that we're adding to the object is just going to be 100 Newton seconds, right? But we know that this is the same thing as 100 kilogram meters per second. So it's like we're adding 100 kilogram meters per second to this box that already had 20 kilogram meters per second squared. So our new momentum, so therefore our P2, we can call it our momentum 2, is going to be 120 kilogram meters per second squared. Okay? So impulse is just when you're adding or taking away the momentum that an object already has. Now, if we wanted, we could use this new momentum to determine the new speed the object is traveling at. Instead of doing that, let's go down to the example, though. Okay, example 1. I would actually encourage you to try this question yourself. You might be able to figure it out just based on those formulas that I've already given you. So pause the video here, try it yourself, see what you come up with, and you can unpause, and I will go through the whole solution. Okay, so if the soccer player kicks a 450-gram soccer ball with a force of 9 newtons, determine the impulse. Well, we know the impulse is just the force times the time that you apply that force for. So in this case, it's just going to be 9 newtons. And, I mean, in terms of direction, it's going to be forward. We'll just say forward. Times the time, 525 milliseconds. Well, a millisecond is 1,000th of a second, right? So that should be times 0.525 seconds, right? And if we do that calculation, you should get 9 times 0.525 is 4.725 Newton seconds. So that's the impulse that we added to the ball. So determine the speed of the soccer ball when it leaves the player's foot, right? So by giving it this momentum, right, we gave it an impulse, which gives it a final momentum of 4.725, right? That's what the impulse does. It adds a momentum. So another way of looking at this is that our P of the ball is 4.725 kilogram meters per second, right? That's the momentum we calculated. But we also know the equation for that is m times v, right? Mass times velocity. So if we know that the mass of the ball is 0.45 grams, we should be able to figure that out. So I'm just going to leave the units out here. 4.725 equals 0.45 times v. We know our units will check out. I put it in kilograms. So all we got to do is divide by 0.45 to get 10.5. So our v is 10.5. Now we did say that the force was forward, so it's positive, so it's also going to be forward. Right? Oh, I forgot to put meters per second. Meters per second forward. Right? So that's how fast the ball is when it leaves the foot. Right? That's really all there is to it. Now, just to make your life a little bit easier, if you ever get a question like this, where you're just adding impulse to an object and then calculating the speed or something from that impulse, one thing you could always realize is that essentially the impulse is just equal to the change in momentum. So if we're setting J is equal to delta P, right? And we know J is just force times time, right? Force times time as a vector. But momentum is equal to, well, just sort of off to the side, momentum is equal to mass times velocity, right? So another way of writing a change in momentum is mass, because the mass doesn't change, times our change in velocity. That's another way of writing a change in momentum. So we can actually just substitute that right into the equation, m delta v, like that. And then we have a relationship where if you know the force, you know the time of the impulse, and you know the mass of the object, you can just directly solve for v within one equation, right? Remember, the object isn't always starting off at a zero velocity, but another way to write delta v is v2 minus v1, or v final minus v initial, right? So you can replace that. If you wanted to solve for an initial velocity or final velocity, you could use that as well. Okay? Two more little things before I wrap this video up. The first one is, this isn't the only way to solve this problem. You could have solved this problem if you'd never heard of momentum before. Think about it. We're applying a force to an object that we know the mass of. We could use Newton's second law to find the acceleration of the object. If we knew the acceleration of the object, and we know it's accelerating for that amount of time, we could use one of our 5 equations of uniform acceleration to determine the final speed of the ball, right? That's the grade 11 way to solve this problem, and you could have absolutely done it that way. But what way is easier? That way or this way, using momentum and impulse? Well, you'll notice we never even have to calculate acceleration here if you're using momentum and impulse. The equations take care of that all for us. So it's actually, the math is actually the same. Behind the scenes, the math is doing the same thing as if you were doing it that way. It's just an easier way to look at it in terms of the equation. Okay? And then the last thing is the question down here. Why are soccer players always told to follow through when they kick the ball? So if you've ever played a sport, not just soccer, tennis or basketball or anything like that, whenever you kick the ball or toss the ball or hit the ball, you're always told follow through. So don't just hit the ball and then stop your foot or stop your hand from hitting the ball. Keep your hand moving in the direction that you want it to go. And the whole reason for that is because how do we get the ball to go faster? What do we do? In this scenario here, what do we do? Well, there's two things we could do. We could either increase the force that's applied to the ball, right? We can't change the mass of the ball, right? If we can make the mass of the ball less, we can increase the speed for sure. But we can't do that. We can increase the force, so that means, you get stronger, right? If you're getting stronger, if you build up your muscles, you'll be able to apply more of a force. And that will obviously give the ball more impulse. But the other way to increase the impulse is to actually increase the amount of time that the ball is being accelerated for. Increase the time of the impulse. So when you're asked to follow through with your foot, for example, when you're kicking a ball, you want to keep the contact time between your foot and the ball as long as possible so that you accelerate the ball for a longer amount of time. Because if we can make this impact time from 525 milliseconds, if we can make it like 700 milliseconds, your foot is accelerating the ball for longer. So you'll end up with a faster moving ball. So that's one of the reasons. There's more than one reason to follow through in any sport, but that's one of the main reasons is you'll get more power, you'll get more momentum put into that ball. Okay, so you can summarize that in your own words.